Okay, so we've just decided that all matter is made up of particles because in order to have the uh, the idea that interparticle forces are going to determine how what the state of matter is, we have to actually have particles. So, uh, in any case, in contrast, consider forces holding the atoms within the particles together. Okay, so in other words, in the water molecule, I have two bonds, right? I have a bond between one hydrogen and the oxygen, and I have a bond between the other hydrogen and the oxygen. And if these forces fail, will the physical properties or the chemical properties of the substance change? And it should make sense that if we break the chemical bonds that are holding the atoms together within the particle, that the chemical properties are going to change. Okay, these are going to be chemical properties that are going to be affected. So, would it be fair to say that the chemical properties of matter depend mostly on the attraction, forces of attraction within the particles? And to that we would say yes, with an exclamation point. Now, because these forces of attraction between atoms within the particles are within the particles, we're going to call these not interparticle forces, not forces between the particles, but forces within the particles. We're going to call these intraparticle forces. Okay, intraparticle forces. So in general, physical properties and changes relate mostly to interparticle forces, while chemical properties and changes relate mostly to intraparticle forces. And I need you to know that. In fact, this might be something that you would write on your graphic organizer. By physical changes, you might write interparticle forces, and by the chemical changes, you might write intraparticle forces. But the thing that's going to help you remember this is that diagram of the 5 water molecules. The dotted lines are the interparticle forces, the forces between the water molecules. Those are what are going to affect the change of state. So interparticles related to physical properties, and then if you break the chemical bonds within the water molecules, those are going to be the ones that affect the chemical changes. And let me just go back to the little diagram we drew real quick to emphasize that again. So if I mess up here, these are interparticle forces, and these are responsible for physical properties or physical changes. And then if I break one of these chemical bonds, that's an intraparticle force, and these are responsible for chemical properties. Okay, so you need to have that understanding. So let's go back to our Nearpod. So that's an important thing to know. Another way to look at this would be to say that a chemical change requires the breaking of chemical bonds and or the making of new chemical bonds, while in physical change, chemical bonds are preserved. So this suggests that if you need to make a statement about whether something is a physical or a chemical change, a good initial approach whenever confronted the need to make this statement is to ask, are the substances the same or are they different before and after the change? So if I heat ice and it turns into water, I still have the same substance, so it must be a physical change. On the other hand, if I take hydrogen and oxygen gas and I cause them to react together, I have a completely different substance, so that's a chemical change. So we'll find that the making of detailed observations during the process can provide some clues. So especially important are changes in temperature. So we're going to go through a list of changes or things that we might observe, a list of observations that will help us figure out whether changes are chemical or physical. Okay, so we do know that all chemical processes are accompanied by changes in energy. Okay, so we have two important terms here. If the process absorbs energy, okay, if it absorbs energy, the prefix or the word that means to go into, the energy is going into the process. It's being absorbed by the process. That's endo, and then thermic means heat. So this means heat going into the process. And if the process sucks all of the energy away from the surroundings, okay, the surroundings are going to get, hopefully this makes sense, the surroundings are going to get cooler or colder. Okay, so if it's an endothermic process and the process is taking place in a beaker, the beaker is going to get colder. Okay, while exothermic processes release heat in the surroundings are going to get warmer. So this is also something that you need to understand. If I absorb energy from the environment's going to get colder, and the process is endothermic. If I have a process that releases energy, it is exothermic. The process is going to, the surroundings are going to get warmer. And I should make the point at this time that, or I should remind us at this point that we've talked about in the past that if I have an exothermic process, that means that the products of the reaction are more stable and require less energy. If I need less energy as products than the reactants did, then I am going to release that energy into the environment, right? That's where the energy comes from. The reactants are less stable and the products are more stable. If I go to something that is more stable, I don't need that energy and it gets released. On the other hand, if I have a reaction where the reactants are more stable than the products, I have to continue to add energy into that process to keep it happening. Okay, now the unfortunate thing is that physical processes are also accompanied by energy changes as well, although oftentimes they're not quite as obvious, but we have to make sure to take into account for other clues too. And so we'll look at a couple of situations here where we have exo and endothermic changes, and one will be chemical and one will be physical, and we'll just give some examples of that here. So let's go to the next slide. And this is going to open a video. And so let's watch this video.
Hey, welcome to the Rochester Museum and Science Center. Thanks for joining us. Today, it's thermite. And thermite's been around since the 1800s. It's a single exchange reaction. You take two different things and you put them together and it makes a new thing. The two things we're going to take today, one of them is aluminum powder or aluminium if you're from the other side of the pond, and the other is just iron rust. So what we're going to do is we've got a little bit of a igniter on the top, and I'm going to take some sulfuric acid and drip it on top of it. When it does, it's going to cause a chemical reaction that's going to superheat this from whatever it is outside right now, somewhere in the 50s, to about 2,300 degrees Fahrenheit in about 2 or 3 seconds. So you'll be able to see a cascade of iron. And then afterwards, we'll take a look at it. Here we go. Ready?
So what you're seeing fall out of the bottom of the container here is molten iron. Okay, molten iron. And later on in the course,
that's all inside there. Once it cools down, we can turn around, crack it open, and you'll have usually little BBs of metal, really bright, shiny metal. This one came out pretty well. Thanks for joining us, and we'll see you next time here at the Rochester Museum and Science Center.
So later on in the course, we'll talk about this particular type of reaction where it's called a single replacement reaction, where the aluminum replaces the iron in an iron compound, and it frees the iron up to be just iron metal. But the reaction was so hot, it was so exothermic, so much energy was released that the iron that was formed was molten, and that's what you saw dropping out the bottom of the container there. Okay? Now, the other thing that we did in class that you're not going to get a chance to see here was that we dissolved ammonium chloride in water. Okay, and this is a physical change. We're just simply separating the ammonium and chloride ions in water. We're dissolving it, and the result of this was that the temperature of the beaker decreased significantly. It got really cold. And this goes to illustrate that we can have physical processes that also have energy changes. So this was not a chemical change. There was no, the ammonium chloride was still ammonium chloride once it was dissolved, but the process itself was a physical process and still resulted in an energy change. So we just want to make that point. Okay. If we go to the next slide, we could have a color change. The color of a substance is closely tied to its chemical nature. Therefore, a color change usually indicates a chemical change, especially if substances were colorless to begin with. However, make sure that a color change is not simply the physical change that occurs when you mix two or more colored substances together. So if I mix red and yellow paint together, there's no chemical change there. The change is entirely physical, but I still get a color change. I get a change from red and yellow to orange, right? So make sure that what you're dealing with, if there is a color change, is not actually just a physical change. Okay, so we're going to have to stop this video here. We're going to watch another video, and before we we'll run out of time if we watch it now. So let's go ahead and stop this video and come back to the next one, and